So why am I talking about this? Why do we care about this graphical method? Well, let's suppose we tried this with a general system of two equations and two variables. And you notice I've got a few axes down here. And I'm not even going to label the axes because I don't want to make any assumptions or restrictions on what the names of the variables might be. So just imagine that you're dealing with a linear system of two equations and two variables, and you want to apply the method that we just went through, okay, in order to solve it. And what I want to look at is when you get to the step where you graph them, what are the possibilities? What could happen? Well, the first thing that could happen is essentially what just happened in the example we just looked at. You could have a situation where the two lines intersect. So let's say one point of intersection. Hopefully I have enough room to finish this. So we've got one point of intersection. Is it possible that two lines don't intersect at all? That's certainly possible. In fact, that'll happen exactly when the two lines are parallel. If we have two lines that are parallel, and I'll remember the notation for parallel lines, you just kind of draw a couple of arrows indicating that they have the same direction. If you have two lines like that, they're never going to intersect. So if that happened to be what your two equations were, like if you had a linear system like this, and then when you go to graph the two lines, you end up with this sort of a picture, they're not going to intersect at all. So there's going to be no point of intersection. That actually means there's going to be no solution. And that's actually what happened in this previous example. If you were to graph these two lines, and you may want to do this on your own time just to check and see what happens. If you were to graph those two lines, you'll see that that's exactly the situation you're in. One of the lines is just a translation of the other line up or down by a couple of units, and the two lines end up being parallel and they never intersect. And in that case, you're going to have no solution at all. So let's just get caught up here. So in this case, you have a unique solution over here if the two lines intersect once. But in the second case, um, you have no solution. No solution at all. What is the third possibility? And you may want to pause this video and just give yourself a moment to ponder it. What is the third possibility? Um, you're certainly not going to have something like this and have two solutions, right? Because why would that not be possible? Well, those aren't straight lines, right? And straight lines can never behave that way. So you're never going to have a situation like that. You're never going to have two solutions. And similarly, you're never going to have three solutions or four solutions exactly, not exactly anyway. But what could happen is you could actually just have maybe the two lines were actually just the same line. But if you look at your linear system, the two equations looked differently. Like maybe one of the equations was just the other equation, but multiplied by two. And that can happen sometimes. And you may not notice it until you actually do the row operations. And then you'll find out that you actually really just have two representations of the same line. So it's kind of hard to draw two lines that are over top of each other. So what I'll do is I'll just use uh, a thicker line. Actually, I could probably do it even thicker than that. A thicker line to indicate that it's actually the two lines are just superimposed over each other. And if that's the case, then you're actually going to have infinitely many solutions. I'm going to better change back here. So in this case, you have infinitely many solutions. And so I put an exclamation mark on the second two cases, so I might as well do it over here as well. So this is case 1, case 2, and this is case 3. There are no other possibilities, and if you don't believe it, well, just spend a few minutes and see if you can come up with a fourth case that doesn't agree with any of these three cases. But the point of this, well, the upshot is, if you have a linear system in two equations and two variables, you're either going to have just one solution. That's what I mean by unique solution, by the way. I mean there's one solution and there are no other solutions. There are not two solutions. There's only one. That's one possibility. The second case is that there are no solutions at all. And the third case automatically is, as soon as if you rule out the first two cases, that means you immediately have infinitely many solutions. So that's the upshot here. Now that our justification here only applies to the case where you have a linear system of two equations and two variables, but I can give you some good and exciting news, which is the following. It turns out that the same phenomenon will happen with any linear system. It doesn't matter if you have 2 variables or if you have 22 variables or if you have 122 variables. It doesn't matter if you have 3 equations, 5 equations, 2 equations, or 97 equations. Any number of equations and any number of variables, you're going to have one of those 3 possibilities. You either have no solution at all, you have a unique solution, which is sometimes you'll just say one solution, or you have infinitely many. So that's what I'll conclude this section with. But that's the upshot. So in the next section, we're going to look at a strategy. We're going to take a look at, I'll keep this short so we can not keep these videos from getting too long, but we're going to look at how do you choose the right sequence of row operations so that you don't A, go around in circles, and B, so you don't take forever to solve these problems, and to make sure that you actually do end up getting an answer every time. That's what the next section is about.